Hello and welcome to another worked example with Dr. Schleif. The graph shows how the height of the water surface at a point in a harbor varies with time t as waves pass the point. Note that we are looking at height against the time t, I want to emphasize to everybody watching this video that sometimes you're going to be looking at distance on the x-axis, and when you're looking at distance, you can read off the wavelength of the wave. But if you're looking at the time on the x-axis, you're not getting the wavelength, you're getting the time period of the wave. And so take care to notice what is being graphed on the x-axis. There are sort of typical paper one questions which will have, which waveform is correctly labeled. And so look for the amplitude to be labeled as such from equilibrium up or from equilibrium down. They like to mislabel that as the entire height from crest to trough, and that's not the amplitude. So don't fall for that trap. Also, look and see, does wavelength correspond to a distance? Because they like to mix up those two. They'll have wavelength, but it's a time. So, well, that's not correct, right? And so only one of those waveforms will be correctly labeled. We'll find an example like that here shortly. But back to the example at hand. You want to be mindful of your P's and Q's, class. What are P and Q? If you have a definition in mind that the amplitude is the maximum displacement, and you see that point P isn't quite at the maximum displacement, but it is displaced, right? A particle of water is displaced that much. So it's a displacement, but not the amplitude. I just spent a lot of time emphasizing that if you're looking at time, you cannot get the wavelength, but rather the time period of the wave. So choice A has both P and Q correctly labeled. Bonus follow-up question, YouTube. Leave the answers down in the comments below. If we know like the time of this wave, let's say there were numbers here and we could read this off, there is something else we could calculate from the time period. In other words, knowing the time period by itself is enough to calculate the frequency, because frequency is just 1 over t, and t is just 1 over f. So knowing the time period gives you the frequency and vice versa. But we cannot deduce the wavelength of this wave, right? Because remember, we're not looking at wavelength, we're looking at time, unless we know something else. So if we're given the time period, we could get the frequency. Well, what else would we need in order to calculate the wavelength? Did you leave it down in the comments below? If you said velocity, then you're correct. You'd have to be told how fast these water waves are propagating through the harbor in order to calculate the wavelength given sort of this time period and the corresponding frequency. Sometimes you'll have a question like this and they won't tell you the velocity of the wave, but they'll give you a clue that it's light. And so light travels at a known velocity, and you're expected to know this. And so that wave velocity equation becomes the speed of light equals wavelength times frequency. It's also part of this course to memorize the wavelengths of the principal radiations of the EM spectrum. So you should know, for example, how long is a radio wave, a microwave, infrared, the visible spectrum, ultraviolet, X-rays, and gamma rays, all traveling at, and you can approximate C as 300 million meters per second, even though it's actually 299,792,458 meters per second. Just use 300 million meters per second for calculations in this course. This has been another worked example with Dr. Schleif. We'll see you next time.